To plan a logistics system effectively, a detailed understanding of the system's requirements is essential. Designing a meaningful system is impossible without knowing how customers place orders, how suppliers deliver, or the characteristics of the load carriers used. All these aspects are crucial as they directly influence the system's design and layout. In practice, requirements can be broadly categorized into qualitative and quantitative. Let's start with the qualitative requirements, particularly the process requirements, which play a central role right from the goods receiving stage. A key initial point is the frequency of goods arriving at the warehouse. This involves understanding supplier delivery patterns, including time windows and quantities. This understanding forms the basis for system dimensioning. Only by knowing the regularity of deliveries can decisions be made regarding the number of goods receiving docks needed and the size of the goods receiving area. Consider the difference between a scenario with one pallet arriving every hour over 12 hours and another where all pallets are delivered simultaneously at 8 a.m. The former allows for consistent goods receiving utilization, keeping a staff member continuously engaged. The latter, however, necessitates a surge in personnel to handle a one-time peak, especially for time-sensitive goods like fresh produce. Additionally, more space is required in the goods receiving area to temporarily store the bulk delivery. Therefore, varying delivery profiles result in significantly different demands on space, personnel, and processes in goods receiving. Equally critical is the type of load carriers used for deliveries. The entire logistics system essentially revolves around load carriers. While often overlooked, a logistics system is invariably planned around the load carriers used. It's not always the case that the load carriers used for delivery are the same as those used for storage, picking, or dispatch. When they differ, repacking is necessary, which can occur at various points within the system, depending on its structure. A simple example is a system where products are delivered or stored, picked, and shipped on Euro pallets. Complexity increases when products are delivered on Euro pallets but picked into small parts containers. This is common in carousel systems, vertical lift systems like Cardex Lift or Logimats, mini loads, shuttle systems, or auto store solutions. In such cases, products must be repacked, e.g., from cartons into standard containers or onto trays, before being stored in the small parts storage system. This leads to further requirements, such as the design and equipment of the goods receiving area, as the technology there must align with the planned processes. Another key aspect in goods receiving is what happens to the goods upon arrival. Are quality controls necessary? Do deliveries need completeness checks? Must items be counted, opened, or inspected? All these factors significantly impact the effort required in goods receiving. The difference between a process where a pallet is simply forklifted into a rack and one where each delivery is unpacked, each package opened, and each item inspected is substantial. Now, I've observed goods receiving processes that were excessively complex, far more complex than economically justifiable. In one instance, a company performed a full quality and completeness check on every delivery. When asked if they regularly experienced issues with suppliers, the response was, "Not really, maybe occasionally, but not often." It turned out the products were very inexpensive. The value of the goods was significantly less than the labor time spent on inspection. Imagine buying a piece of butter at Lidl or Edeka, and then taking it to the National Metrology Institute to have it weighed and its molecular structure analyzed, just to ensure it matches the packaging exactly. Probably no one would do that. If the butter weighs 5 grams less, it's annoying, but economically irrelevant. However, the situation differs when purchasing expensive machinery, a car, or a house. In those cases, comprehensive inspections are standard. But in the aforementioned case, extremely low-cost products were being inspected with a labor effort exceeding the potential loss from a defective delivery. Such examples illustrate that we must precisely understand when and why inspections occur in goods receiving. Does everything need to be checked in every shipment, or only spot checks? Do products need to be scanned individually? Is repacking required? Does documentation or photography need to be done? Are there requirements for maintaining cold chains? Must temperature data be checked upon goods receipt? For temperature-sensitive products, such as certain foods or pharmaceuticals, this can be critical. Even a brief interruption in the cold chain can compromise product quality. In these cases, temperature checks are mandatory. And this inspection requirement, in turn, affects the process, equipment, and personnel in goods receiving. A vivid example is chocolate. If you store chocolate at excessively high temperatures, around 18 or 19 degrees, a gray film can form on the surface. This looks unappetizing, but doesn't alter the taste or shelf life. Nevertheless, many customers perceive this as a quality defect. Providers of high-quality chocolates therefore place great emphasis on controlled storage, often at precisely 18 degrees Celsius. Some warehouses even establish a chocolate tent, a segregated area with constant temperature control. Such requirements must also be considered in system planning. It's not enough to know the products. You must know the conditions under which they can be stored. Do certain goods need to be stored in a refrigerated area? Are there products that can be stored at room temperature, but not above 22 degrees? Which zones must the warehouse have? In addition to temperature-controlled products, another crucial product category must be considered during planning: hazardous materials. These include flammable, explosive, or toxic substances, among others. Such products cannot simply be stored anywhere in the warehouse. They must be kept in specifically designated and often legally mandated storage areas. Furthermore, the maximum storage quantity within a storage section is frequently limited. These specifications arise from safety regulations and must be strictly adhered to. In modern warehouses, compliance with such regulations is typically supported by a warehouse management system, WMS. As soon as a product is received into the warehouse, the system suggests a suitable storage location based on its properties and considering all relevant parameters. However, this only functions reliably if the warehouse is digitally managed. Unfortunately, warehouses still managed with Excel or even paper lists are encountered in practice. Such systems are prone to errors and reach their limits when faced with more complex requirements or higher volumes. Another point concerns the load carriers used, not only for delivery, but also within the warehouse and during dispatch. It's not always the case that the same carriers are used in all process steps. For example, a product may be delivered on Euro pallets, picked in reusable containers within the warehouse, and finally repacked into cartons for shipping. Each of these changes incurs effort, takes time, and increases the likelihood of errors. Therefore, it's essential to understand why these changes occur. Are there valid reasons for switching load carriers, or has it simply evolved historically without being questioned? In warehouse planning, the existing process should first be thoroughly understood, and then considered whether and how it can be improved. One goal is to minimize the number of so-called product touches. Each time a product is repacked or repositioned, it not only incurs costs but also creates potential for errors. If you find that products must be handled multiple times, the question automatically arises: is this necessary, or can the process be simplified? This often concerns how customers are supplied. Are they supplied in cartons, or is the use of reusable containers possible? Reusable containers have the advantage of being more stable, reusable, and often better suited for automation. However, they also require return logistics and incur investment costs. Again, the economic context must be understood. The more uniform customer deliveries are, the more efficiently the overall system can be designed. Another significant aspect is the shipping process. This also influences the warehouse layout, particularly the outbound area. Does the company ship via parcel service providers like DHL, DPD, or Hermes? Or does it use freight forwarders who handle entire pallets or partial loads? Is there an in-house vehicle fleet, or do customers pick up their orders themselves? These questions directly impact the organization of the shipping area, time profiles, and picking urgency. For example, if a freight forwarder has a fixed pickup time and completion is delayed, additional costs may arise, or the delivery is postponed. Parcel service providers, in turn, pick up shipments at fixed cut-off times. Failure to meet these deadlines results in missed pickups, as drivers do not wait. In contrast, an in-house fleet theoretically offers more flexibility, although a tight schedule is often still necessary for economical route planning. One point frequently overlooked in the outbound area concerns the sequence of provided goods. In many cases, it doesn't matter if packages are provided in a specific order. This is the case, for example, when working with parcel service providers. There, packages are placed on roller cages or containers, the container is picked up, and the sorting center automatically arranges the correct delivery sequence. Thus, the order in the warehouse is irrelevant here. However, the situation is quite different when pallets or containers are shipped via freight forwarders or with in-house vehicles. Let's say a truck holds 33 pallets. If a specific pallet needs to be unloaded first, it must be loaded last in the truck. This is referred to as reverse loading in reverse unloading order. This means that the sequence of pallets in the outbound area must be precisely planned and maintained. And the warehouse must prepare accordingly. This logic can also apply to smaller vehicles such as vans or sprinters. In such cases, the warehouse must not only pick but also sequence, which requires either clear processes or automated support. In addition to the specific logistical requirements, the fundamental question arises: are we planning a new system in a new building or within an existing building? In the first case, we speak of a so-called greenfield project. There, the degrees of freedom are large. The building can be designed as required by the system. However, this also involves many decisions because a lot of options are open. In contrast, brownfield projects involve planning within an existing building. There are often limitations due to existing structures, such as walls, support grids, ceiling heights, or fire protection regulations. You have to work with what's there, and that can sometimes severely limit the solution options. An important keyword in this context is the building's floor plan. How is the building cut? Where are the gates? What is the clear height? The maximum usable height for racks or automated systems? In many cases, high storage would be theoretically possible, but stricter fire protection regulations apply above a certain height. For example, sprinkler systems, including water tanks and control technology, must then be installed. Sprinkler systems are expensive to install and operate. Some companies, therefore, deliberately choose to stay below a certain height to save effort and costs. This must also be considered in the planning phase. Another criterion is the load-bearing capacity and condition of the floor slab. Is it an area where an automated system will later be installed? Then requirements for flatness, load-bearing capacity, and surface quality are very different from a warehouse where only manual forklifts are used. Especially for storage and retrieval machines, automated guided vehicles or shuttle systems, a precisely executed floor slab is essential. Even small unevenness can lead to disruptions there. Finally, the question arises as to how flexible the system is with regard to future growth. Can the system be expanded within the building? Are there structurally provided reserves? Or can the building itself be expanded, for example, by an extension? Does the adjacent land belong to the company? Or would it have to be acquired first? Is the purchase realistic? Or could it fail due to ownership or municipal regulations? All these questions influence the strategic design of a system. If it is foreseeable that a system will need to be expanded in the medium term, and this expansion is realistically possible, you can initially plan smaller and more cost effectively. If, however, there are no expansion options, the system should be dimensioned as completely as possible for the expected final utilization. Another important aspect concerns the ergonomic requirements of the system. These depend heavily on the products being handled and the environmental conditions under which this occurs. At room temperature, many activities can be carried out without problems. However, in a deep freeze warehouse at minus 28 degrees Celsius, completely different conditions apply. There, products can no longer be handled with bare hands. Employees wear thick gloves, have limited motoric skills, and can only stay in the warehouse for a limited time. There are clear legal requirements for how long people can work at such temperatures, as well as mandatory break times. In addition to the legal framework, occupational health and safety regulations play a role, and in many cases, the requirements of the Works Council or collective agreements. What does this mean for planning? A system that works at room temperature cannot simply be transferred one-to-one to deep freeze conditions. Processes, technology, and personnel deployment must be adapted to the physical strain. In many cases, this leads to an increased degree of automation, such as through automatic conveyor technology, automatic picking solutions, or robot-based palletizing. But even then, certain interfaces remain that must be carefully designed to minimize the strain on personnel. All these considerations show that when planning a warehouse, we must not only consider technical metrics. It is not enough to know the number of orders or the required storage space. You must understand the context in which the warehouse is to operate. What products are being moved? Which customers are being supplied? What temperatures prevail in the warehouse? What legal and social conditions must be observed? What risks exist, such as from hazardous materials or temperature-sensitive goods? Of course, this list could be significantly expanded. There are countless qualitative requirements that can play a role in warehouse planning, depending on the industry, product range, and target system. It would be neither sensible nor possible to map all eventualities in a general checklist. However, the principle is important. Planning a warehouse requires a deep understanding of the actual operational reality. Only when we know how a company works, why it works that way, and what requirements result from this, can we design a functioning future-proof system. In addition to qualitative requirements, quantitative requirements must also be considered during system planning. This involves measurable quantities, data, volumes, and temporal distributions. A warehouse cannot be meaningfully dimensioned if we do not know how much needs to be moved there per hour, per day, or per week. We must understand how many orders are processed, how many picks are performed, how many cartons are packed, and how many loading units are shipped. These key figures are the basis for determining space, technology, and personnel requirements. However, it is not enough to look only at total volumes. A classic mistake I observe in many companies is the use of averages. For example, they look at how many orders are processed per day and divide this number by the number of working hours. This results in a seemingly logical assumption. If we have 12,000 orders per day and work for 12 hours, we must handle 1,000 orders per hour. This sounds simple, but is rarely correct in reality, because in most cases the workload is not evenly distributed throughout the day, especially in systems with a high proportion of private customers, i.e. in the B2C business, there are strong fluctuations. People do not order evenly throughout the day. They order in the evening after work, they order on weekends, they order when it rains outside, and they prefer to stay on the sofa. This means that a large part of the orders arrives outside of warehouse working hours. These orders are then collected and often released for processing the next morning. Now, in such cases, a strong load peak occurs, especially on Monday mornings or after public holidays. I remember a company where particularly many orders came in on Sunday evenings. On Monday mornings, thousands of orders were waiting for picking, and the parcel service came at 2 p.m. for collection. Everything had to be packed and ready for loading by then. Before 2 p.m. it was hell. After that, it was comparatively quiet. Anyone planning with averages in this case is far off the mark. The critical period is not 12 hours long, but perhaps only 4 or 5 hours. During this time, the system must deliver full performance. This is precisely why it is so important not only to look at daily volumes, but also to analyze the time profiles behind them. And this applies not only to order volumes, but also to pick numbers, packaging units, and shipping volumes. These values also fluctuate throughout the day, and in many cases even throughout the week. We often see typical patterns where the order load is particularly high at the beginning of the week, while towards the end of the week, more warehouse processes such as put away, replenishment, or inventory are in focus. Another crucial aspect in warehouse planning is the order structure. Without a clear understanding of how orders are structured, no meaningful picking warehouse can be designed. It makes a significant difference whether a typical order consists of a single order line with a single piece, or whether it consists of 50 order lines, each with 20 pieces. These differences significantly determine how the picking system must be designed. For example, if a warehouse serves both business customers and private customers, a bimodal structure often results. Business customers order large quantities, many items, high piece counts. Private customers, on the other hand, often order only 1 or 2 items, frequently in single pieces. Anyone who tries to form an average from this makes a serious mistake. In this case, the average does not accurately reflect either of the 2 real order classes. For example, if the average is 5 order lines with 5 pieces per line, this value does not really apply to any customer group. Neither the business customer nor the private customer typically orders exactly like that. If you plan a system based on this average, it will function suboptimally for both groups. Therefore, it is essential to consider the order structure in segments. Who orders what, at what frequency, with what depth? Are there seasonal differences? Are there customers whose orders are regularly bundled? Are there minimum order quantities or specific item combinations? All of this affects the choice of system, i.e., whether zone picking is useful, whether batch picking can be used, or whether a goods-to-person solution would be economically viable. Another point that must be considered in this context is the assignment of orders to storage areas, the so-called systems fitting. Imagine a supermarket warehouse with different temperature zones, a room temperature area for durable products like pasta and rice, a refrigerated area for dairy products, a fresh area for meat and fish, a frozen area, and possibly even a separate fruit and vegetable area. Each order that comes in must now be divided into the corresponding storage areas based on its individual items. It is important whether a product is picked as a complete pallet, as a packaging unit, a so-called case, or as a single piece. For example, If an order contains 10 packs of pasta, they may be taken from a case, which in turn is on a pallet. Another item, such as a toothbrush, might be taken individually from a large carton. Depending on how granular the picking is, different picking areas are needed. In many modern warehouses, especially where automated systems are used, different system areas are also set up for these different requirements. This can mean that fast-moving items are automated and a single-piece picking is done manually, or that containerized goods are processed differently than palletized goods. To operate a warehouse economically and efficiently, it is essential to analyze the item structure in detail. Two particularly helpful tools for this are the ABC analysis and the XYZ analysis. The ABC analysis looks at the volume value share. It helps us understand which items have a high share of total sales or total movement in the warehouse, i.e., how strongly individual items contribute to the total volume. The XYZ analysis, on the other hand, looks at the regularity of demand. It classifies items not according to their volume, but according to how regularly they are requested or ordered. Both analyses, taken individually, already provide valuable information. However, in combination, they unleash their full potential. For example, if an item is both an A item and an X item, i.e., frequently and in very regular quantities demanded, it is a so-called high runner. Such items are particularly suitable for automated picking systems or for just-in-time delivery with low inventory levels. Because if I know that I need exactly 1,000 pieces of item XY every day, I don't have to permanently store large quantities of it. I can agree on fixed delivery intervals with the supplier, such as a daily delivery at the same time. This allows inventory to be reduced without jeopardizing the service level. This may seem counterintuitive at first glance. One would think that frequently demanded items should also be in stock in large quantities. But the opposite can be useful, especially with predictable high-frequency demands. It is more economical to align supply with regular deliveries and keep inventory as lean as possible. A completely different picture emerges with C items with a Z character. These are items that are rarely requested, and when they are, in irregular, poorly predictable quantities. Such items incur high storage costs if you store them in large quantities as a precaution. At the same time, a stockout can be critical in certain cases, such as with spare parts for machines or plants. Here, other strategies are needed: safety stocks, alternative sources of supply, or a combination of warehousing and procurement logistics. The combination of ABC and XYZ analysis thus provides a differentiated view of the item range. It helps to decide which items should be stored in which warehouse areas, which are suitable for automation, which need to be stored particularly space-saving, and which can perhaps even be outsourced or procured on demand. It is no coincidence that these two methods have been standard equipment in the logistics toolbox for decades. And you will find that if you later work in a company that is responsible for logistics processes, you will probably use these analyses again and again throughout your professional life. In addition to the ABC and XYZ analyses, there are a multitude of other analyses that can be significant for the planning and design of a warehouse. We will also discuss how to derive meaningful key figures from raw data, which data can be extracted from an ERP or WMS system, and what to consider when working with incomplete, noisy, or erroneous data. Because one thing is clear, the reality in companies is rarely as clean as a textbook suggests. There will always be cases where data is missing, where old bookings distort the statistics, or where processes run differently than they are documented. Therefore, it is all the more important that you learn to deal with these uncertainties, to form hypotheses, to critically question data, and to formulate concrete recommendations for action based on your analyses. Because the goal of all these analyses is not the analysis itself. The goal is to enable informed decisions for system design. It's about understanding how many picking locations are actually needed, how high the storage capacity should be dimensioned, how many employees are required in which shift, which technology is economically viable, and how flexibly the system can react to future changes. The slide you see in front of you is therefore deliberately divided into two parts. On the left side, you will find a selection of qualitative requirements. On the right side, a selection of typical data analyses. Both areas interlock. You must understand processes and be able to make sense of the data simultaneously. Only when both come together can you design a system that works in everyday life, economically, robustly, expandable, and tailored to the needs of the company. In the next units, we will practice together using example data how such analyses are structured and interpreted. You can find the corresponding raw data in the e-learning platform. You can take a look at it in advance if you wish.